Now let's look at an example where it's not the case. So we start with really one of the terms in a partial fraction decomposition. So it's already a partial fraction. So one of these simpler terms, right? Supposedly. But this is the case where we have just a linear function over the square of a irreducible quadratic term. Indeed, this is an irreducible quadratic term because if you calculate b squared minus 4ac, you get 1 minus 4, negative 3, you get something negative. So we cannot factor that any further. So in that case, if we follow the steps we've indicated, we would start with completing the square at the bottom, which means that we look at x squared plus x and we identify that with x plus 1/2 of the coefficient of x, in this case 1/2, that we square, and then we subtract this square of 1/2. So in other words, we obtain x plus 1/2 squared minus 1/4 plus 1 inside our square at the bottom. Of course, 1 minus 1/4 is 3/4, so this is what we obtain. And now the next step is to make a substitution where u becomes whatever is under the square. And then we're going to have to replace x plus 1 in terms of u as well, but if u is x plus 1/2, then that means x is u minus 1/2, so when I add 1, I get u plus 1/2. So we obtain u plus 1/2 over u squared plus 3/4 squared. Then we split the fraction, as we have already done. It's u over u squared plus 3/4 squared plus 1/2 of 1 over u squared plus 3/4 squared. And so now this is what we need to integrate with respect to u. The first term is not going to be a problem because we can proceed by substitution. We let v be u squared plus 3/4. Then dv is really just 2u du, so what we have at the top, u is, well, this u du is 1/2 dv. So we end up with 1/2 integral of dv over v squared plus 1/2 integral of du over u squared plus 3/4 squared. The first term is not the problem, but the second one is one of these cases where we need to use trig substitution. So this is where we're going to have some serious work to do. So we have a sum of squared, right? U squared plus a positive number. And so we're going to use a trig substitution, u equal a tangent of theta, where a is the root of this positive term 3/4. So namely, u is going to be square root of 3 over 2 tangent theta, where theta is restricted to the open interval from negative pi over 2 to pi over 2, to make sure that tangent is 1 to 1 on that interval, and we'll be able to use the arctangent. Then du is root 3 over 2 secant squared of theta, so we can replace du by this quantity and u squared by 3/4 tangent square theta. Pulling out the root 3 over 2 from the du, this is what we obtain. You see that here I wrote explicitly what the integral of dv over v squared is. Of course, this is the integral of v to the negative 2, so you get v to the negative 1 over negative 1. In other words, negative 1 over v. When multiplied by 1/2, you get negative 1 over 2v. Then we have 1/2 multiplied by root 3 over 2, and then we have a secant squared at the top, and at the bottom, inside the parentheses, 3/4 tangent squared u, which is u squared, plus 3/4, all that squared. Okay, now, if I replace v by its value, v was u squared plus 3/4, and I replace u by its value, so now 1 over 2v is really 1 over 2 times x plus 1/2 squared plus 3/4. On the other hand, when I multiply 1/2 by root 3 over 2, I get root 3 over 4. And then if I pull out the factor 3/4 outside of my square, I get 9/16. And inside the parentheses, I now have tangent square theta plus 1. And the whole point of this trig substitution is to get this expression tangent square theta plus 1 to appear, because this is equal to a square, namely the square of secant theta. What we have inside the parenthesis in the first term is really the form where we have completed the square of our original irreducible quadratic term x squared plus x plus 1, so I can rewrite it that way. On the other hand, if I pull out the 1 over 9 over 16 and write it as 16 over 9, I can pull that in front, and then I have secant square theta at the top, and at the bottom I have secant square theta squared, in other words, secant theta to the fourth. So that cancels out as 1 over secant square theta, but since secant is 1 over cosine, what we have is really just cosine squared. So this is what we obtain after cancelling this 16 over 4 as just 4. So we have now an explicit part of the function plus a constant times the integral of cosine square theta, and we know how to integrate that. Namely, to integrate an even power of cosine, we're going to use a double angle formula and replace cosine square theta by cosine 2 theta plus 1 over 2. After pulling out the factor 1/2, we're going to obtain for an antiderivative of cosine 2 theta 1/2 sine 2 theta, and for an antiderivative of 1 just theta. Of course, when I pulled out 1/2, I obtained a 2 instead of a 4 in the multiplicative constant in front. Now this sine 2 theta is a little bit of a problem because we want to at the end obtain a function of x alone without any theta left, because we're looking for an antiderivative of our original function of x, and we want that as a function of x. We have a clearer correspondence between theta and u than between 2 theta and u, so I'm going to replace sine 2 theta by 2 cosine theta sine theta, but since I'm multiplying by 1/2, what I obtain is really just cosine theta sine theta plus theta. And now we need to look into transforming things back in terms of x. So we look at the trig substitution we've done. We had u equal root 3 over 2 tangent theta. In other words, 2 over root 3 u is tangent theta, or theta is arctangent of 2 over root 3 u, because we are in the proper interval for theta to apply the arctangent. And what does that mean in terms of cosine theta and sine theta? Well, we're going to use the type of geometric representation we have used to go back to the original variable when we were looking at trig substitution. Namely, we see that since tangent theta is 2u over root 3, that means that the ratio of the opposite side to the adjacent side in a right triangle is 2u to root 3. Using the Pythagorean theorem, we see that the missing side would be root of 4u squared plus 3, but u was really just x plus 1/2, so we can replace u squared by x plus 1/2 squared, and multiplying things through here we obtain root of 4x squared plus 4x plus 4 for the hypotenuse. Now cosine will be the adjacent side root 3 divided by the hypotenuse root of 4x squared plus 4x plus 4, and sine will be the opposite side 2u, which we can write as 2x plus 1 because u is x plus 1/2, divided by this same hypotenuse, which is root of 4x squared plus 4x plus 4. So we obtain this expression where I multiply root 3 and 2x plus 1, and each one have these same denominator root of 4x squared plus 4x plus 4. So when we do that, we end up with this expression because, of course, the product of the denominators end up being the square root squared, in other words, whatever is under the square root. We could simplify that a little bit further with the constants and so on, but here we have an explicit function of x as an antiderivative of our function x plus 1 over x squared plus x plus 1 squared. Now keep in mind that here we started directly with one single partial fraction to integrate. In general, it could be that we have several of these to deal with. So when the irreducible quadratic term is repeated many times, things get technically difficult, even though theoretically there is a systematic way to deal with them. So now that we have gone over all the different cases, it is time for you to do some homework.